And this can be static or it can be kinetic friction. And we talked about different cases there. Of course, you don't have to memorize any of these mu's or anything, or you may have to calculate one, but you don't have to memorize it for an input. I'll give you whatever you need, okay? All right, so there are particular cases, and the other complication that we introduced was studying something on an incline. Okay, so you're given an angle, and you have some object sitting on there, and it's moving either, it can be moving either up or down the incline, okay? So if you just let this thing go, of course it wants to go down. The easiest thing always is to draw the weight straight down because you know the direction of that, okay? It just simply makes a right angle here. And then if you draw a perpendicular to the slope, this is the normal force, which is what you need to calculate the friction. And that's opposite a component of the weight, and this turns out to be that angle. So by now you should be quite familiar with chasing these angles around. This component of gravity turns out to be mg sine of the angle, and this one mg cosine of the angle. Okay, and I'll give you the usual sine and cosine vector projection diagram on the formula. Okay, so then the frictional force, if the motion is this way, then the friction opposes the motion, so the frictional force would be up here. Okay, so a good diagram is always helpful because you should be able, if you draw this, which is basically a free body diagram for this one object in this case, if you draw this correctly, you should be able to read off from there the sum of the forces that goes into the second law, if you've done the drawing properly, and included all the forces. Okay, okay. So for these, I mean, Chapter 5 involves second law calculations, turning on friction where we didn't have it before in Chapter 4, but also putting things on a slope and combining things being moving on a slope with friction. Okay, so that's the essence of these calculations. So what I want to do for this review is to basically just focus you on these particular topics in each chapter. Okay, I'll take some questions later if we get through all these chapters about these practice tests. Okay, but they're good examples in each of these practice tests of these calculations. Okay. All right. We also in Chapter 5 discussed circular motion. Uniform circular motion. So something going around in a circle at a constant rate around the circumference. Okay? And so that the radial acceleration is d squared over r. Okay? This is a derivation that you should be able to do. Okay? Remember the similar triangles argument here. Okay? So that's one of the derivations you're expected to do. We then combine things like friction and circular motion by, say, the example of a car going around a bend. Okay, so you have a car, this is the center of rotation, this is some R here, okay? And remember that the frictional force acts towards the center, and because the car is going around at a constant radius, this is actually static friction. Okay, because the car is not moving along the radius, although it's moving along the road. But we're not talking about the motion around the road, we're talking about the possibility of moving along a radius here. Okay, okay. And this is related then to this v squared over r for the acceleration. Okay. So the second law comes in different forms. If you write F is equal to ma, then it can be that a radial force is equal to a mass times v squared divided by r for this particular type of problem. Okay? And those are really the main elements of this Chapter 5 that are focused on for the test. There may be some of these optional or different, slightly more challenging sections in these chapters, but if I don't mention it in this review, then it won't be on the test. Okay? All right, so that was Chapter 5, which is more Newton's law type problem. For Chapter 6, we went over to talking about gravity and Newton's universal law of gravity. It says the force of gravity is equal to Newton's big constant, and of course give you the value of this mass 1 times mass 2 over the distance between them squared. So this applies to any two objects wherever they are in the universe. This thing has an infinite range, okay? Because you can always make this as large as you like, but it never quite goes to 0. Okay, you should be aware of Newton's argument remember he made this argument, which is related to this one over r squared. Okay? He took the Earth and the Moon and the gravitational attraction, and he calculated the acceleration, the radial acceleration of the Moon towards the Earth. Okay? And then correlated it with the square of the distance. Yep.
So the radius, that would include their distance from the center to the surface as well?
Yeah, you should be. I mean, some of these problems like satellites, you have to be aware of the Earth's radius, then plus the distance from the surface out to the satellite. So, but usually the problem makes that clear. Yes.
We're going to be given those numbers like the gravitational constant and all that.
Yes, absolutely. Right.
Do we have to do it at the center of the Earth, or is
Well,
the
if
surface
you're doing the Earth to the Moon, then you're given a number, and it's implied that it is from center to center.
Okay.
But if you have a problem which is near the Earth, then it makes a difference if you add the radius of the Earth in or not. Right. I mean, if you're calculating little g at some altitude, right?
Right.
Then it really makes a difference.
Okay, yeah.
Right. Okay. Related to this, we talked about weight and weightlessness. Okay, remember we did this example of an elevator. So you imagine that you have a sort of spring scale in an elevator, and this is attached to some mass, M. So this has a weight mg. So the weight that you measure is the weight that this object, with which this object pulls down on the scale, which is the same as the reaction of the scale pulling up on the object. So this is W here. And if this has an acceleration A, right, then you can generally write down that W minus mg is equal to ma. Okay? And then this, whatever this turns out to be, is the apparent weight. So, the effect is if you feel that you're going down in the elevator, it feels like you're lighter because the floor is going away. Or if you're going up in an elevator, you feel your weight's going up because you're pushed up more by the normal force. Okay, so remember the set of problems that we did with this. Okay. So there's three conditions basically. Is the elevator going up? So then the apparent weight goes up, the elevator goes down, W goes down. Okay, if you're in free fall, then you're weightless and W is equal to 0 because you're falling down with the acceleration G. Right? Yes.
So if you're going up, then it's W minus mg?
Well, you have to do it the right way around. Yeah, for this object, right, then I'm implying that you're going upwards.
And if you're going down, it's W plus mg?
Yeah, but remember you can write the equations down either way, then interpret the sign of the result of the acceleration. Okay, the acceleration has a sign on it, plus minus. Okay, so be careful when you write it down.
So you can write it this way for up or down, but it's just a sign that changes?
Yes, but it's usually, there's a better way to do it. I mean, if you're told it's moving upwards, draw the arrow upwards, right? Yeah, because otherwise you'll confuse yourself. Yeah.
So if A is 0, is it just empty? Or is the whole game 0?
Well, when W is equal to 0, right, then the acceleration is going to be equal to minus g. Just, you fall down, it's like you were just, anything was falling under gravity.
What is W again?
W is the apparent weight.
And is that given, or how do you calculate it?
It could be given, and then you're asked to work out the acceleration or the other way around. Yeah, right. Yeah, I mean, any of these, any piece of physics for which you can write an equation, I can give you one part and ask you to work out the other, or the other way around. I mean, yeah, that's the nature of setting these problems. But W is the apparent weight, okay? So if the accelerator is going up, you feel heavier, right? People feel, so you'd expect W to go up and be more than this, right? So if you move this over the side, you get W is m into g plus a, right? So then if it's an upward acceleration, then the apparent weight would be greater than mg, and vice versa if you're going down. Okay, all right. Okay, we also talked about satellites and planets. Okay, so again, this is Newton's law. So force is mass times acceleration. For this, okay, the gravitational force is like g m big M over r squared is equal to little m v squared divided by r. Okay, so this applies for the moon going around the Earth, or a satellite going around the Earth, or the Earth going around the sun. Just insert the correct masses. Okay, but you notice the little m appears on both sides, so it usually cancels. And we were able to show, if you introduce into here, v is equal to 2 pi r divided by t. So if you think of a circular orbit, this is the circumference, this is the time to go around once, the period. Then the velocity is just the distance divided by the time. If you put that into there, then you obtain this relationship between t squared and r cubed, which is the basis of one of Kepler's laws. So that's a derivation that you should be able to do, but it's just basically combining this equation, which is a version of the second law for something in circular motion under the influence of gravity, and you're inserting this equation for v, substituting this in here, and it gives you a t squared because you got v squared. Okay? And when you cancel the various r factors, you get r cubed. Yes?
What is that equal with t?
Sorry?
What is t squared over r?
Oh, it turns out to be equal to 4 pi squared over g times big M. Okay, and then you notice that for any given system, like our solar system, right, this is equal to a constant. Because this would be the mass of our sun, and g is constant. Right, so that's the basis of Kepler law, is that the square of the period over the cube of the distance is a constant for a given solar system. Right.
So can we just look at it as t squared, and it is understood that that's a constant when deriving that equation? Or do you actually want us to substitute t squared with?
Well, it depends on the nature of the problem.
Okay.
I mean, you can give you that law and then ask you to figure something out about the period of a satellite around some, a planet around some other star, for instance. Okay. Right. But yeah, for any, for any solar system, you put in the mass of the star, right, and this is a constant.
Right.
It's going to be different constant for every different star and solar system.
Yeah.
But,
Yeah.
yeah. But the t squared over r cubed will still hold. On the assumption that the law of gravity holds everywhere. Right. Okay, so that's the basis of chapter 6, right, for calculations of gravity. Okay? And, in terms of weight, we're going to talk about weight as well. Weight, remember that what we call the weight is actually a force of gravity, so it's g, m, big M, in this case the Earth, over r squared. Okay, so and you cancel this and you get an expression for little g. And we did calculations of little g at the top of a mountain or far away from the Earth. Right? So you should be able to evaluate how this thing differs from our standard 9.8 meters per second squared, given some other location. Okay. Okay. So then we moved on to chapter 7, which was to do with, it introduced the concept of work and energy. I'll go back over here. Okay, so chapter 7, we introduced first the idea of work. Okay? And we defined an amount of work to be, well, a dot product of a force times a displacement, which is Fd times the cosine of some angle. So if you're trying to move something along a surface and you're pulling on it with a force which is at an angle, it's only this component, F cosine theta, in the direction of the displacement d that counts. So you have to be very strict when you're talking about work in the physics context, that this is the definition. Okay? So it's the force component in the direction of the displacement multiplied by the displacement in words. Okay? We also talked about the amount of work done by a varying force. And there was an example in one of these practice tests of that, of some robot arm, I remember. So then you integrate F dot dl. What you're doing is then saying you're going along some path like this, and you're dividing this up into little steps of delta L, and there's some force component here, and you're taking this F delta L, and you're taking the sum over these, is what the integral does for you. Okay? And you may have to make some transformation of variable in order to be able to actually do the integration. We saw some examples of that.
Is that when we have like an object falling from like very high distances from the surface of the Earth? That the
Yeah, that was a reasonably complicated example of that, right? There was a simpler example where you give an expression for the force in terms of the displacement and they integrate it on one of the practices.
Oh, okay.
Yeah, I'm not assuming any great knowledge of calculus beyond simple integration and differentiation for this case. Okay, then we talked about the work kinetic energy principle. The relation between these things. Okay, so this is another derivation where you can imagine that an object is accelerated from some velocity v1 up to v2. So we know that v2 squared is equal to v1 squared plus 2 acceleration times some distance. Okay, so the acceleration is just the difference of these squares over twice the distance. So then if you take the work as being equal to a force times the distance, and then, so this is equal to a mass times an acceleration times the distance, then you can put this into here, okay, and get m v2 squared minus v1 squared times d all over 2d, and then this gives you a half m v2 squared minus a half m v1 squared. And then we chose to identify this as something associated with an object moving with a velocity v1, and called that the kinetic energy. Okay? Okay, and remember, the kinetic energy always has this expression. The potential energy depends on the force that's acting, and we'll come to that in a moment. So, straightforward calculations of work out of a fixed force at a certain angle, a varying force where you're given the formula, or using the work kinetic energy relation. Okay, what is the work required to stop an object moving at a certain speed? Well, the work done is just the negative of the kinetic energy, right? You're taking away all that kinetic energy until the thing stops. Therefore, you're doing work in a negative sense, bringing this thing to rest, and it must be equal to the negative of the kinetic energy. So it's a powerful principle in order to be able to calculate work in certain circumstances. Okay. So then we want to talk more generally about energy and energy conservation.
So work is the same as change of kinetic energy, right? Wait, so is
Yeah.
work pretty much the same as the change of kinetic energy?
Yeah, I mean, well, it depends on the context, on the problem, right?
Okay.
But yeah, I mean, like an example, if you have an object moving along, and you say, how much work do I have to do to stop that object? In other words, reduce its velocity to 0, right? You're obviously doing work in the opposite direction
Right.
to its motion, so
Right,
it's
so
the
it
negative
would
of the
be
kinetic.
equal to the kinetic energy.
Right.
Okay.
I mean, as long as there's no other loss of energy,
Right.
right? You got to be careful, right? Yeah. I mean, if something was sliding to a halt as you were stopping it, you'd have a loss of energy from friction, and you have to take that into account as well, right? Okay. So then, chapter 8 was to do with the conservation of energy. As a physics principle. Okay? We talked about conservative and non-conservative forces. Okay, so the characteristic of these is that the work done is independent of the path. Okay, so examples of this are gravity, okay, the electromagnetic force, which obviously come to in a different class, but there is a number of these that are independent of the path. And non-conservative force, of course, the classic example here is friction, because the path that you take depends how much you slide over, what distance you slide over, and therefore the different paths have a different energy loss to friction. In order to talk about the overall conservation of energy, then in addition to kinetic energy, we had to introduce this other topic of potential energy. So this is energy by virtue of position or configuration. So the classic example here is, okay, here's the surface of the Earth, here's the mass, and I lift this thing up in the air. Okay? So what I do is I give this some potential energy. Okay? Remember, it doesn't matter where you call the zero of potential energy. It's only this difference of energy that matters. Okay? So you can put the zero of potential energy somewhere convenient for any particular problem that you solve. Okay? What you're doing here, of course, this thing has a weight. So you have, in order to lift this thing up, you have to have a force which is constant velocity is equal to the weight in the opposite direction. So you have a force which is going up, lifting this thing, right, which would be equal to mg. It's going over a height h, therefore the work done would be equal to mgh. You've done that amount of work. What you do is you give that object the same number of joules of potential energy by virtue of the fact you've lifted it up in the air. Okay? Because you can drop it down and it can do work, say driving a nail into a piece of wood or whatever you want to do. So if you lift this thing up, you give it potential energy, you release it, it will then have kinetic energy and can actually do some work when it gets down to the bottom. So this was our kind of classic example. So we gave, there's another example in here, like of a bungee jumper. So this is a good example because there's no kinetic energy involved in the beginning and the end. So the bungee jump, you have a situation where somebody has a cord, it's slack to start with, and they're going to jump. Okay, so they have some sort of potential energy to start with due to gravity by being up in the air, and then they jump and the cord is stretched. Okay, so that potential energy goes away, but then you store potential energy in the cord or spring or whatever it is. So in this case, you're going from some sort of mgh over to a half kx squared, which is what we derived as the stored potential energy when you have a spring that's stretched or compressed. So in this case, you have no kinetic energy to start with because somebody's waiting to jump, they're not moving. And when they get to the bottom of this fall, there's no kinetic energy here either. So what you're doing is trading one form of potential energy into another form of potential energy. Okay? So the number of joules here better equal the number of joules over there. Yeah?
The number of joules for mg on the side, does it equal the number of joules mg plus 1/2 k x squared?
No, in this case, you could set this directly equal to this, right?
So is there a actual energy?
Well, you're implicitly assuming that the potential energy is zero at the bottom of the fall. Here. Yeah, right. So more correctly, the change in gravitational potential energy goes into the energy stored in the spring. I mean, the joules have got to go somewhere. They've got to be conserved, right? There's no other leakage of energy in this problem. So what you had by this person standing up on a bridge or whatever before they jump is pure potential energy. There's no kinetic energy. And that better appear somewhere at the end. So when you get down and this thing is fully stretched, then all the energy is then stretched in here. Of course, then they rise up again, of course, right? But for just considering top to bottom, it's a straight transfer of different types of potential energy.
So potential energy in that case would never be zero, because you have the fall and then you have the cord gaining potential energy, right?
Yeah, and you know, what happens? I mean, it goes back up again and sort of oscillates, and it will settle down to somewhere where the cord was sort of stretched under the weight of the object or the person, right?
Right.
And then they still would have some potential energy because they'd be off above the zero potential energy.
Yeah.
But that's a more complicated problem. Okay, and don't forget then, if you have a problem where you have something like friction, right, then you have to account for that. So the total change in kinetic energy plus the total change in potential energy plus the change or the effects of non-conservative forces like friction, the total change is equal to zero. Okay. And another way to say that is that you can't absolutely create or destroy energy. The joules have to be accounted for somehow. So you can have them transferred from kinetic into potential, potential into potential. If some object is sliding over a surface, then you've got to account for the energy lost out of this problem due to friction and take it into account in this sum. So for instance, if you have an object which is sliding down a slope, you know that if this thing just slides down, then you had some sort of mgh up here, and you had a half mv squared here. If you have friction as well, you won't get the same number of joules here appear at the bottom, because somewhere you actually lost some energy to friction on the way down. So this number of joules, whatever that turns out, the number turns out to be, would not equal this number when you have some loss in the middle, right? But that's simply what that equation means. You have to account for all of this stuff.
Yeah.
Right. Yes?
Would that be a trick question? I still don't like, because like, then you go from potential to kinetic, right? But then technically you're also throwing potential in. So like.
Well, it's a straight trading of one sort of potential energy for another. I mean, imagine also you have a situation like this, where you have a big spring and you have a car and it runs into the spring, right? Okay. So this has a certain kinetic energy. It hits the spring, and at the moment where the spring is fully compressed, you've just traded all that energy for the potential energy in the spring, right? In this case, it's just potential to potential. Here it's kinetic to potential. You're accounting for that energy going somewhere.
Ooh, so it's potential to potential?
Yeah, this one is potential of gravity to potential of a cord. Because the kinetic energy here, I mean, if this guy is just standing on top or near the bridge, he's not moving. There's no kinetic energy, right? When this thing gets to the bottom, momentarily it's at rest before it goes up. So the kinetic energy here is also equal to zero. So what you've got left is potential. Okay, but it's a different sort. You've released the potential energy due to gravity. If I let this thing fall down, it releases that energy, right? In this case, it has to go somewhere. The only place it can go is into stretching the cord, and therefore it's stored in the cord. And we derive that expression for the potential energy of, for a spring or a cord. Okay? Yeah. Okay, all right. So then the final chapter, was a change to talk about momentum, okay? And what I will do with chapter 9 is to only go into the simple collisions part of that, because there are some other aspects of like two-dimensional collisions and some more complex things that I will not put on the test. So let me just indicate the basics of this. And some of this we have done homework on. I will just cover the first part of this. Okay, so chapter 9 on momentum. Okay, remember, first of all, momentum as a vector is defined as the mass times velocity. Do not confuse this with a half mv squared, which is the kinetic energy. Okay? All right, Newton's second law. He actually wrote down as the sum of the forces is equal to the rate of change of momentum, which is dp over dt. If you put this into here, then this is equal to dmv by dt. And if you take the differential of a product, this looks like mdv by dt, okay, plus v dm by dt. I've got two terms. This is our basic ma. So this is what we get usually in these textbooks simplified from this more general formula down to forces, mass times acceleration. But there is this term that if you have a varying mass in the problem, then Newton's form of his second law accounts for that variation as well. Okay. However, for this test, then I'm going to focus on the conservation of momentum in simple collisions. Okay. So if we have two objects, A and B, and they're colliding, and then they bounce off like this, okay? And we label this velocity A, velocity B, velocity A prime. Prime usually means after the collision, okay? Then we can write down the sum of these objects, so MA plus MB is equal to, this is the sum of the momenta before the collision, is equal to MA VA prime plus MB VB prime. Okay? This covers a multitude of different types of collision. So we can have the simple two bodies colliding like I drew there. It also covers a situation where we have something like an atomic nucleus which splits. It's sitting there, it emits some sort of particle like this, and then you have a nucleus prime. Even though this has no momentum to start with, if you add up the momentum of this guy, and they're plus and minus, then it should come to the momentum of this, which is zero if it's just sitting there. Okay? It also covers a situation where here's the Earth, and here's the dreaded asteroid, and it hits the Earth and gets absorbed into the Earth, right? It covers that situation as well, okay? Or it covers a more mundane situation where you have two football players, one tackles the other and holds on to the guy so that they're momentarily together, and you have to take their combined mass. So it covers, this equation covers a number of situations like that, okay? The only other topic in chapter 9 that I will consider is impulse. Okay? So if we have, this force is a rate of change of momentum, you can write this as a change in momentum is a force times t. And the idea of using this is then to define this quantity as an impulse. So this was equal to J, I believe, in the book, or sometimes it's called I. The point of this is that if you can calculate a change of momentum and you know the time interval over which that change takes place, you can calculate a force involved. And we saw an example of jumping down from 3 meters down from a roof, whether you bend your legs or you don't bend your legs. Okay? And it's used by automotive engineers to calculate the magnitude of the force that the structure of an engine has to resist in a collision so that it protects the passenger compartment, for instance.
Wait, are you saying that equal to joules, meaning equal to work?
No, J is a symbol for impulse.
Oh, okay.
Forget joules. In this case, it's nothing to do. Yeah, it's usually called, I usually call it I for impulse. For some strange reason, they changed the J in this book, just to confuse everyone. Yeah, J is a symbol for total angular momentum in atomic physics as well. Right. We only have a certain number of characters in the alphabet. Okay, so what I've covered here are the essential topics, okay? So if you see a section which is not covered on what I wrote down here, it's not going to be on the test. Yes?
So what would the questions look like for impulse? Like find the impulse of...
Oh, yeah, I mean, there's a question in the book which says, look, a tennis ball is coming in and it's going to bounce off a racket, okay? And it takes 70 milliseconds to bounce off it, right? And its velocity going in is this, its velocity coming out is this. So you've got a change of momentum, right? And you've got a time interval. Therefore, you can take the ratio of the change of momentum to the time interval and give you the force on the strings on the racket.
Oh, okay.
Yeah. It's just using this sort of reworked expression for Newton's version of the second law to evaluate the force in a certain situation. So it's probably more intuitive if you write this thing as like an average force is equal to the change in momentum over the change in time. So if you can figure those things out from the information you're given, then you can get an average sort of force. Yes?
So if it was a tennis ball question,
Yeah.
you would just take the mass of the tennis ball and the velocity,
Yeah.
and give you...
Remember, the velocity vector turns around when it bounces off, so you have to get it the right way. The signs.
So would you have to subtract the two? So you would do...
You'd have to subtract the two, but one would have a minus sign. So they end up adding together. Be careful.
Okay, so you add the momentum of it going this way?
But you got to say this is the plus
So
x direction,
let's say
right?
it's going at like 10 meters per second at the
Yeah.
person, and
Yeah.
goes back at 5 meters per second?
Sure.
And the tennis ball weighs 1 kilogram?
Yeah.
What would be the momentum?
Well, then you'd write down this expression that, so you'd have 10 meters per second, right, going in, and then this thing comes back out at 5 meters per second, okay? So, and if it, well, 1 kilogram is a kind of hefty tennis ball.
Or
It's a
something
bowling ball.
Probably break the
It's
racket.
an easy number, yeah.
I don't know, whatever it is, okay, so you have m times this and m times this, okay? But the delta p, if this is the plus x direction, right, it would be m times well, it's final minus initial, so it's m times 5, which is minus, but it's going to be, to be careful. Yeah, then minus m times 10. You should get them adding together. The change of momentum, they add together, in this case. There's look at the level 2 problems for this chapter 9 in the book. There's several examples of that, including one where something bounces off a wall at an angle like this, okay, where you have to take this component going in and this component going out. So there are wrinkles on these problems. Yeah?
So there's not going to be any angular stuff or
Oh, the angular, no, that was chapter 10. The rotation and stuff. Yeah, I figured that'll be on the third test.
Professor,
No, this is only up to chapter 9 on the first part of it. Yes.
do we know how to use density in order to find the radius of a planet given the same mass as another planet? On the
There is a problem like that. Yes.
so,
yes.
but how do we manipulate density? Because I saw you did an equation to find the radius of a certain planet.
Oh, that was one of the practice ones, right?
Yeah. I just
hang
didn't know
on.
what equation that was.
Density is mass over volume.
Yeah.
That's not what he used over there.
Hang on. I remember it well. Here we go. So this, yeah. So what it said was that this planet Europa had the same density as the Earth. Okay. So rho is equal to mass over volume, which is like a 4 pi r cubed, right? Okay, so what we're saying is then, up to factors of 4 pi, the mass of this planet Europa over its radius cubed is equal to the mass of the Earth, okay, over the radius of the Earth cubed. And you know this, I guess you know this, and therefore you can actually determine the size of this planet. That was the point of that. And then you take that and you feed it into the expression for gravity. I mean, the point was then to find a g prime, right? So remember, mg prime is equal to g m, big M over r squared, right?
Right. And
This
we
cancels. So you solve for the cube root of this and you put it into here.
I understand that, but how do you change the 4 pi into just that?
Oh, it's a ratio. It's a ratio. The 4 pi cancels.
The 4. Oh, okay.
You got 4 pi. I mean, I have 4 pi here and I have 4 pi in the denominator here, so I can just.
Oh, okay. Yeah, makes sense.
Yeah. Right. So it's simply a ratio.
Yeah.
Yeah. Sorry, it's not a wonderful work of art. Yes.
The asteroid one, how does that work for bounce? If it doesn't bounce back?
The which?
Like, there's a question on the homework where it's like, if the asteroid's like starting out like 9 meters per second.
Oh, it combines with the Earth?
Yeah.
Yes. Well, then the final momentum is the velocity of the combination times their combined mass. Right? So for the case where they stick together, you've got like an m1 v1 plus an m2 v2 is equal to an m1 plus m2, right, times some common velocity v. That's true for anything. That's true for the two football players tackling each other and becoming a combined mass momentarily, right? Or the asteroid hitting the Earth and they stick together. Yeah. So that's one version of a collision problem. Yeah.
In the question, we didn't have mass. That was a homework question.
Oh, it depends. Well, it depends on the particular nature of the problem. Sometimes there's some common mass that drops in. But I'll try to make it clear. But what will not be on the test is that more complicated stuff where we derive formulas for elastic collisions and more complicated inelastic collisions. Okay, it'll be just simple collisions. Okay? All right, any other questions? All right, so it'll be the same format. I'll give you all the formulas. I've been through these, I've solved these problems. They actually have solutions. That was a joke. And I've tuned up the formulas. So, but if you think you need something, ask Garrett, and he should be able to tell you. Okay? And then we will go over this not next Monday, but next Wednesday. All right. Thanks.